Our next speaker is Chris Schubert. Chris is works with the USGS, and he will be talking to us about understanding the changes in groundwater and surface water expression on Long Island. Chris?
Thank you. Okay, great. Good morning, everyone. It's nice to see a lot of familiar faces out there and nice to be in person. There we go. Great. To jump things off, I'm going to talk about a neat new depiction of the water cycle that USGS developed for educators at all levels. And so it's kind of nice to start out at the 300,000 foot level before I zoom in a little bit onto the Long Island aquifer system. And then I'm really going to get to what is the topic of today's talk, which is how groundwater and surface water are really inextricably linked in our groundwater-dominated landscape here. They're really one resource. And this photo is a great way of thinking about that. If you've ever dug a hole into a beach near the shoreline, you've created a window into the water table. And so there you have surface water and groundwater side by side linked together. I'll also talk a little bit about how water moves through those systems. A topic that's really, I think, relevant to this group today is the effects of water table changes on surface water features that are really important for habitat. And then wrap things up by kind of talking about the current trajectory of where things are in our groundwater and our surface water resources. So here is that new take on the water cycle. It's something that USGS put together a couple of years ago, and they really strove to make something that was both accurate and effective in terms of communicating principles. One of the neat things about this is it fairly clearly and consistently differentiates between the pools of fresh water globally and the fluxes or the pathways, the ways of how water moves between those pools globally. And the one that I really want to kind of highlight, because it's kind of a common thread in this talk, is the atmosphere and precipitation, which really drives everything in the water cycle, especially on Long Island. One of the other advents of this new depiction of the water cycle is our previous ones really didn't treat human use of water very effectively. And so really part and parcel of this one is getting into the really varied ways that water touches our lives. And it may not be obvious to folks here, but most of these forms of water use are actually in play on Long Island, with the exception probably of fracking and hydropower. The other thing that this new depiction does is it gives a much better treatment of groundwater. And here we have a nice depiction showing how groundwater is expressed below the surface and the ways in which how groundwater resides and how it moves in the system is affected by human activities. So I really do encourage folks to go to it, play around with it. There are a variety of media. There are large scale posters. There are smaller letter size 8.5 by 11 depictions. It's multilingual, and there are even versions that have spaces for folks to write in their terminology in their own tongue. So pivoting to where we are today in the Long Island aquifer system, this is a kind of a neat three-dimensional depiction of the system that some folks may have seen. One of the things I really need to emphasize here, though, is this is really, really greatly exaggerated vertically on the order of several tens of times. In reality, it's a pancake, but it is a system that dips to the southeast, dips toward the Atlantic, from the mountainous highlands to the west. We have three main aquifers in that system: the upper glacial, the Jamico-Magathie, and the Lloyd, and those are separated by two intervening confining units that impede the movement of water through those aquifers. They are the Gardiner's Clay, which is not continuous across all of Long Island, primarily along the South Shore. And we have the Raritan Confining Unit, or the Raritan Clay. And that is fairly extensive across Long Island, but it varies in thickness and it varies in its effectiveness as a confining unit or something that retards groundwater movement. Here's just a blow up in 2D of one face of that 3D block diagram we were just looking at. Shows the same thing that I just pointed out in the previous one. But what I really want to just kind of highlight here is where the upper glacial aquifer goes from a fully saturated aquifer system, which is in blue, to the unsaturated system. Whoops, my bad. Unsaturated system, which is shown here in brown. So that is that level where we go from unsaturated to saturated, that is the water table. It is across most of Long Island within the upper glacial aquifer. There is a small area in the West Hills area of town of Huntington where the Magathie aquifer extends a little bit higher up, and so the water table is within those older sediments. But if you think of the upper glacial aquifer, think of the water table aquifer for the most part. So, back to this concept of groundwater and surface water resources on Long Island being one linked resource. I hunted around a bit to find a nice graphic that really brought it home that our surface water features on Long Island are really just examples of where land surface dips below the water table. And so you now have a window into that aquifer system. And that aquifer system is essentially just the ground where it is fully saturated. And what that looks like on Long Island is in this diagram on the right. We have grains of clay, silt, sand, and gravel mixed together in various combinations. And where they are fully saturated, that is the water table. There is, of course, moisture in that unsaturated zone. Of course, that's where trees put their roots down. That's how they tap their moisture. But where you hit that fully saturated level, that is the water table. We don't have underground rivers. That's not to say that there aren't locations around the world where we've got caverns, lava tubes, ice tubes, where water can move through. And here's a quick example of what that might look like in a fractured rock system, say in the Appalachians, on the left here. But on Long Island, think of us living on a sponge that is fully saturated at the water table level. So what does that mean for surface water resources? Well, if we look at the thickness of that freshwater aquifer system, we have two different depictions of it on the left and the right here, and they're playing up different concepts of how water enters the system, moves through the system, comes out of the system. Two important considerations. One, and that is the vast majority of our surface water features on Long Island are groundwater fed. Water is actively moving from the aquifer system into these surface water features. Virtually all the flow of our surface water streams and the water that flows into our wetlands and our ponds in natural conditions is coming from the aquifer system. It's coming from groundwater seepage or groundwater base flow. In unnatural settings where we've got impervious surface, yes, some of the precipitation that would come down and hit land surface and normally would percolate into the ground if it's not transpired by trees or evaporating, flows overland and will enter these surface water bodies. And that amount of overland flow does increase with the amount of urbanization we have on Long Island, particularly up island. And so a greater amount of flow in those surface water features in the urbanized areas is coming from runoff. The other important consideration here is that these surface water features are really only dipping into a fairly small portion of the aquifer system. So as a result, changes in the level of water in the aquifer system can have outsized impact on the extent of surface water features that are fed by them. And we'll talk about that a little bit more in a minute. So here are some examples of effects of water table changes on surface water features on Long Island. These declines, think of when the water table falls and groundwater levels fall, where are these going to be most apparent? They're going to be most apparent in shallow groundwater features. So think broad, shallow lakes, think wetlands. Here are some great examples from about a decade and a half ago. Lake Ronkonkoma on the left, Lake Panamoka on the right. And you could see that we have tens, if not hundreds of feet or meters of difference between the current lake shoreline and what we might call the normal lake level. Conversely, when we're in a period of above normal groundwater levels or a higher water table, where would we expect to see that? Outdoors, we'd certainly expect to see it in low-lying land areas adjacent to these groundwater-fed lakes, streams, ponds, wetlands. But an important consideration comes into play here in terms of our infrastructure, much of which is installed during periods of normal water table elevation, or sometimes, if you unfortunately had a home built in the early to mid 1960s, built when the water table was depressed because of drought. And what happens then when the water table returns to a more normal position, or when we have above normal levels in the water table, we have an example of that on the right here, you can have basement flooding. And as some people here probably know, much of the subterranean infrastructure in Brooklyn and Queens, think of subway tunnels, think of deep basements for industry, for hospitals, in many cases was put in when the water table was artificially depressed by the overdevelopment of groundwater resources in those two boroughs. And because the city now relies exclusively on the upstate reservoir system for drinking water, those depressed groundwater levels have rebounded. And so much of the subway system, many of the deep basements in Brooklyn, Queens, are now actively facing groundwater flooding and have to be actively dewatered to keep them dry. So moving more toward the end game here, we want to talk a little bit about the current state of the aquifer system. I mentioned the importance of precipitation. Essentially, precipitation is the sole natural source of fresh water to replenish our aquifer system. Here we're looking at a depiction of precipitation with some examples of the highest and lowest recorded levels over the period of a water year, which is really the period that hydrologists and meteorologists tend to look at annual and longer-term changes in water resources. So the water year runs from October through September of the following year. It's named for the year in which it ends. Here we have examples. Again, the x-axis here is from October through September. We have the 2024 water year shown here in the green line and the area under that curve. We also have here the normal long-term water level, that's in brown. And we have those years, those water years, when we recorded the highest cumulative and the lowest cumulative precipitation. So 2024 in green, the highest was 1986, I believe, if I can read that right here. Maybe it's 89. Sorry, it's a little pixelated for me. And the lowest is 2005. And one of the things I want to point out, we get a lot of questions about why are pond levels so low one year, maybe another year it might be, why is my basement flooding? I've never had this in my home. So much of this is driven by precipitation, and it's also driven by when the precipitation falls. The vast majority of recharge to the aquifer system occurs during the non-growing season, when we don't have high levels of evaporation, when we don't have high levels of transpiration by plants, forests, et cetera. So in 2024, starting in October of 2023, we could see that we were actually quite low. We were close to the lowest rate of replenishment in our record here. Then we went to a period that was actually quite higher than normal through the spring of the 2024 water year. And then with the exceptions of in May and August, it really, really leveled off. And I don't show it here, but that leveling off has continued. Another way to look at this is the Palmer Drought Index. This essentially represents a way of looking at surpluses versus deficits of moisture. Both this depiction and the previous one are really based on data from Long Island MacArthur Airport. And so if we look back beyond just the 2024 water year, if we look back the last 10 years, we could see that we had these oscillating periods of dry and wet and dry conditions. One of the things we also are starting to notice too, this may be a sign of a changing climate, is the switch from one to the other can be a little bit steeper. And we see that in particular in 2020 when we go from quite wet to quite dry, 2021, and again in 2024. So what does this look like in our aquifer system? Kind of following the same theme here of showing time on the x-axis, again, looking back about the last 10 years. What we're looking at here is groundwater level changes in the upper glacial aquifer, the water table aquifer. Here we're in southeastern Nassau County, so a fairly urbanized part of the island. It's an area that's sewered. It's an area that's seen long-term groundwater level declines because the water that is withdrawn from the aquifer system for drinking water supply and other uses is not returned to the aquifer system through on-site systems. It is actually shunted off to our centralized wastewater treatment facilities, and ultimately it permanently leaves the system through outfalls to the ocean. And so what we could see is we started out the period in a more of a normal condition in about 2015. We had this multi-year decline. Again, it mimicked the Palmer Drought Index. We went to a somewhat above normal conditions around 2020, 2019, again, somewhat near normal conditions for the next couple of years after that. Another decline around late 2022, 2023, much above normal conditions in 2024. And this is important for where we are right now. We start this dry period that we've entered in the last 6 to 9 months in a period of surplus. Here's looking at a similar data set now from Suffolk County. This is at a well near BNL. Again, want to point out where we started, more or less near normal conditions, that multi-year decline in the late teens, higher than normal conditions around 2020. Again, a decline through 2023, and then a rebound again in 2024. Pivoting to stream flow. I mentioned earlier that virtually all of our surface water features on Long Island are groundwater fed, and that's especially so for our streams. Here we're looking at stream flow, again, from southeastern Nassau County, a highly developed portion of our system. Same 10-year period across the x-axis here. Just want to point out that while the trace, the observation of stream flow is in green or in red where the record was estimated when this was printed out, there's also another trace in there, and that is that yellowish orangish trace, and that is the long-term normal flow. In this case, it's from a record of almost 80 years on Massapequa Creek. And again, we see much the same pattern, although we don't see the same highs and lows. And that is because of how streams behave and their connection to the aquifer system. So we can see these declines in the late teens. We also see the decline here in the 2022, 2023 period. But we don't see, with the exception of maybe a little bit in 2020, too much of above normal conditions. And that gets back to the long-term declines that we've seen in parts of the island that have been sewered. And in 2024, we're really just getting back to the long-term normal level, although in late 2024, we can already see we're starting to drop again. Moving a little bit east into an area of intermediate development. And so now we're showing the Connecticut Brook in south central Suffolk County. And so we're starting to see a pattern that now mimics what we see in the water table a little bit more closely. We see that multi-year decline in the late teens. We see the above normal conditions around 2020, normal conditions through the early 20s, 22, 23 decline, above normal conditions in 24, and getting back down toward normal late 24. This is starting to show us a little bit of how it's a double-edged sword, right? We said that surface water features, think of them as the canary in the coal mine. They are very sensitive to changes in groundwater declines, but also being groundwater fed and having the amount of water that's in storage in a groundwater system can allow them to buffer a little bit those shorter term climatic variations. And so we see that in some of the streams like Connecticut, where they're not quite as insensitive immediately to decreases in precipitation, as one would expect if we were off Long Island and our stream flow were primarily sustained by runoff. And lastly, here we're looking at stream flow in a minimally developed part of Long Island. This is the Peconic River, the Riverhead area. Not unlike what we saw at Connecticut Brook, the multi-year decline in the late teens, above normal conditions around 2019, 2020. The declines in the 22, 23 period, back to near normal conditions in 24. And then lastly, I just want to wrap up on this figure here, which is a great way of trying to get a finger on the pulse of what conditions may be like in your area of interest. This is a depth to water map. It's an online mapper. The points on here represent monitoring wells that we used and actually preparing this depiction. The colors here, the warm colors, the hot colors, those represent areas where you may have a groundwater flooding hazard. With the hottest color, red, less than 11 feet, think of the floor of a basement. This is an area where you might have issues with groundwater flooding. The cooler colors, think of those areas where groundwater flooding hazards are lessened, strongly mimicking our topography on Long Island. So the moraines, the more higher elevation inland areas, we have less of an issue with groundwater flooding. What you can do is you can click on these maps. It's an interactive mapper. You can click on either the dots or the background. If you click on the background, you get an estimate of the depth to water at that location. So the difference between land surface elevation and the top of the water table. If you click on one of the dots, you'll actually pull up the record for the monitoring well used in the depiction, and you could see the period of record for it. And so here we have an example from out east. And we've clicked on a water table observation well, and same type of depiction. It's a little cut off here in the slide, but you've got time here on the x-axis, and I believe this one goes back to the 70s. And then on the y-axis, you've got both the depth to water on one side, and you've got the water level elevation on the other side, which is important from an infrastructure and engineering point of view, or if you want to compare it to sea level. And I think with that, here's my contact info. All these slides have information as to where you can get more information on any of these depictions or in any of these concepts. Again, ending on my really favorite figure about how you can really put your finger on the pulse of an aquifer system by digging a hole at a beach and creating a window into the water table. And with that, happy to take questions.
Staying in my hometown. Can you hear me?
I can now.
In my town, we get water from the Lloyd Aquifer, I believe it's called, North Shore. I've seen it, but I don't know how far north it goes. I'm always seeing just the sliver of Long Island. How far north does the Lloyd Aquifer go?
So the Lloyd, the overlying Raritan confining unit, and the overlying Magathie aquifer date back to the age of the dinosaurs. They're Cretaceous age deposits, quite old. And so they've been exposed to millennia of erosion and deposition and glaciation. Because they are southward dipping, those units are much thicker. The further south you go, they're much more vertically extensive. The further south you go, they actually pinch out on the North Shore or underneath Long Island Sound. And that area of where they pinch out or have been eroded away is quite irregular. And you see lots of examples of where erosion from glaciation or perhaps erosion from Pleistocene, fluvial, riverine erosion has carved out portions of those Cretaceous deposits, including the lowermost one, the Lloyd. But you mentioned the Lloyd. For those that don't know it, the Lloyd is really set aside in New York. It's set aside on Long Island for coastal communities that don't have potable freshwater supplies in the shallower aquifers. And so it's really reserved for the Barrier Island communities, for the peninsulas on the North Shore that don't have abundant, high-quality freshwater. But as you may or may not know from your water supplier, because it's a deep confined aquifer system, water takes a very long and difficult, tortuous path to replenish it. So as a result, even though that water is old and clean and unimpacted by superficial contamination, it's very sensitive to being overpumped or overdeveloped. And so it is kind of the poster child for saltwater encroachment or saltwater intrusion on Long Island because of that sensitivity to overdevelopment.
So there was one other point, there is water we're getting on Long Island that comes underground from Connecticut. Is that true?
I've heard that more times than I care to remember. It is an urban myth. There is no underground river. In most parts of the world, there are no such things as underground rivers. You can have underground caverns. You can have ice caves, you can have lava tubes, and these can be fully saturated and water can flow through them. But in the vast majority of the world, groundwater is in the pore spaces between grains, sediment grains, or it's in the fractures and faults that exist in bedrock areas.
So there is no water flow in these aquifers. It is where it is, and it doesn't get replenished except for groundwater that seeps down into this deep area.
Correct. The water on Long Island, and here if you look in this block diagram, you could see the more lightly shaded area. That's our freshwater resource, and it is bounded at the bottom by bedrock, which is really the floor of the aquifer system. The bedrock has very, very little water in it. You can also see that it's bounded laterally, not just by the surface waters of Long Island Sound, the Atlantic Ocean, South Shore Estuary, et cetera, but there's salty water that extends below those surrounding saltwater bodies and extends all the way down to bedrock. So we really are a freshwater lens of our own here. We have no connection to the mainland. And so that freshwater lens sits on bedrock in the interior of the island, but it sits actually on top of salty groundwater as you get to the north and south shore and out to the east end.
And one of the pine barrens is supposed to have a lot of pure groundwater available.
Yes.
Is that being used other than locally?
Well, it's sustaining natural resources. It's sustaining the surface water features out there. You know, there are a lot of coastal plain ponds, kettle hole ponds, some major streams on Long Island trace their headwaters to the Pine Barrens, certainly lots of wetlands. And there is some water supply development in those areas. You know, that was obviously part of the enabling legislation for the Semper Pine Barrens, which was to reserve these, to protect these water resources for potential future needs.
And Beaver Dam in the Oyster Bay, Locust Valley area is constantly fed water from underground. Can you explain that?
Well, those would be groundwater springs. That would be groundwater seepage from the aquifer system. So again, just think of these streams that we have on Long Island as areas where land surface has been incised into the water table. And if the water table stays permanently higher than the level of those stream channels, it's going to permanently supply fresh water to them.
So they're being fed by groundwater in the surrounding area to be Beaver Dam?
Correct. You're welcome.
Have you seen changes? There it is. Have you seen changes in the intrusion of salt water with the rise of sea level due to climate change? And that's something I think that maybe I'm right on Great South Bay, and I see trees are starting to die from the top up, and I'm wondering if their roots are starting to be killed by the salt water.
Yeah, there are examples of ghost forests up and down the East Coast. You know, these were areas that were primarily, freshwater dependent habitat that have seen increased levels of salinization, whether it's from storm surge, episodic storm surge, or whether it's been more chronic exposure to salt water, a rising of the water table. I did some work with the National Park Service out on Fire Island, and that was one of the things we were looking at, was the extent to which the freshwater lens is responding to sea level rise. When we think about the water table can respond pretty quickly. And, I showed a lot of graphs here that show oscillations that are happening in almost, a fairly short period of time, responding to changes in precipitation, responding to changes in seasonality, think growing season and non-growing season. But the ability of that zone between freshwater and saltwater move is a much slower one. You're not necessarily just sloshing the water back and forth which can respond pretty quickly, like turning a hose on that's already filled with water. You're now talking about dissolved constituents actually having to move through the aquifer system. And that is a much slower process. So while we think that we may be seeing it in areas, it is one that's going to be a lagging indicator, and it's going to take us longer to discern. The flip side to that is areas that have historically been intruded with saltwater because of overdevelopment, they're very, very slow to flush that salt back out. Think of soap in a sponge, very difficult to get out.
One
You're
last
welcome.
question, really quick.
Yeah, I've been looking at in the Pine Barrens lately for the headwaters of the Seatup Creek. And for some reason, it's not there. And I've been walking all over and on the maps, I'm there. And I can see the back, kind of like a drainage, but it's gone.
That is a really great observation. What you're looking for is the start of flow of that stream. And we've been talking in general terms of how changes in the height of the water table affect whether water is flowing into a stream or not flowing into a stream. But that stream channel is not planar, right? It's got a headwaters and it discharges somewhere downstream. So where the water table intersects that stream is the start of flow. When the water table is lower, that start of flow is going to move downstream. When the water table is higher, that start of flow is going to move upstream. And that's a really important diagnostic to understand where the water table is. And we actually collect that information and we map it.
Well, to me, that was pretty important.
Yeah.
because I was moving south on that, trying to find it. And I was going across this Otis Pike quite a bit. And
Yeah.
there's a lot of farming in that area. And I'm wondering if they're withdrawing.
Odds are they're pumping water, they're going down just deep enough to consistently get water. They're not going down any deeper than they need to because it costs money to go deeper, right? So they're pumping water from the water table aquifer. So during times of precipitation deficits where they've got to make up more of their crop needs from pumping, they're going to pump more water and they're likely going to depress the water table further. You're welcome.
Thanks,
Right.
Chris.
Thank you.